All right, while people are trickling in, I need one reminder. I know that in the previous lecture this morning, I promised to get back to something tomorrow, but I don't remember what it was.
Okay, welcome back everyone. We now have a little lecture from Elisabeth, and then we go straight to tutorial by one. So Elisabeth, please.
Yeah. So I'm just trying to figure out, because there was a question this morning that I promised to get back to tomorrow, but I don't remember what it was. What was it? Okay, let me write that down that I don't forget again. All right. So we have talked about how to go from catalogs to summary statistics. And now the remaining step to be all set up for tomorrow's tutorial about the bus reanalysis is this step of going from summary statistics to parameters, and in particular to parameters that we can trust, both in terms of the mean and uncertainty. So somehow we have to compare our data to the model and figure out how to get the error bars. So for that, of course, we need to do statistics and be clear about what we mean by probability. And while, as most of cosmology, I will largely talk about Bayesian parameters. Okay, good. Well, I will mostly talk about Bayesian inference here, which is the most common way of doing this in cosmology at the moment. At times, it's good to be able to switch from one perspective to another to question our results. So I will briefly talk about both. I will briefly also talk about frequentist methods for parameter constraints. So in that frequentist approach, we see probability as frequency. And thus, so then the probability of an event is the number of times the event occurs over the total number of trials in the limit of an infinite series of equiprobable repetitions. In this case, the model is fixed, but the data are repeatable. While in the Bayesian approach, probability is a degree of belief about a given proposition. So here the data are fixed, and the model is repeatable. And there's a really nice review Bayes in the Sky going into many details of that I would recommend for fun reading, contrasting these two perspectives in a bunch of different cases. So let's just take the Hubble constant as an example. If we say it's 72 plus minus 2, then the frequentist would interpret it as performing the same procedure with independent data will cover the real value of H0 within the limits of 68% of the time. Of course, that's not very practical in cosmology, where we can't just go to a different part of the sky again and measure the Hubble constant, given where we are now. That would probably require far intergalactic space travel to get a sufficiently different sky at this point. While the Bayesian would interpret these numbers as the posterior distribution for H0 has 68% of its integral between 70 and 74 kilometers per second per megaparsec. This posterior can be used as a prior for future analysis of independent data. So let's first dive into Bayesian inference, where our goal is to, at the end, determine the posterior of some parameters given data in the model. And for that, we use Bayes' law, which is really just a restating of basic probability. And that allows us to relate the posterior to the likelihood of the observed data given the parameters and the model. And then the remaining ingredient is the prior of our set of parameters, again, conditional on the model. And that basically just means that what you know after the experiment, your posterior, that is what you knew before or prior, plus what you learn in terms of the likelihood. And of course, that means now we will need to be really intentional about both the prior and the likelihood. So the priors quantify what you knew about the parameters before the experiment, and that come in a bunch of different flavors. This can be information from previous experiments, theoretical limits, but some part of it may also be subjective, and our preferences will enter these priors. But what really matters at the end for inference, of course, is the product of prior and likelihood. So in regions where the likelihood is 0, your prior doesn't matter for the parameter estimation, but it can still be relevant for model selection, which we'll get to later. And in cosmology at the moment, it's very common practice to use uniform priors on most parameters, which is of course easy to write down and easy to code up, but hard to justify. Basically, any analysis that says, well, we'll use a prior on omega m from 0.2 to 0.4 or whatever, sure, that is something that is broader than most current constraints, but can you just really justify how you chose either of those two limits? So if there's no clear justification, then it's really important to do sensitivity analysis afterwards. That is to change your priors and check whether that changes the conclusions. Especially as I was in charge of DS cosmology analysis, I feel one of the worst things that we did in that collaboration was to use super broad, uninformative priors. I think we go from omega m of 0.1 to 0.9 in our likelihood analyses, and in general also use other stupidly broad parameter priors, which causes a lot of problems and gave a lot of headaches also to other people trying to repeat our analyses. So that's one of our hard-earned lessons. When the original motivation simply was that we really just want to check what we get from weak lensing and photometric clustering alone, not relying on CMB priors to really compare these two experiments. But of course, it's really hard to compete with CMB measurements on NS or theta star. So those priors can be actual lifesavers in multi-dimensional inference. Of course, it's also important to keep in mind that a uniform prior in one parameterization may not be uniform in another. That is probability mass is conserved, not density. And when we transform to new variables, we have to take care of the Jacobian. Yeah?
So a couple of slides prior, which showed the evidence likelihood relationships. Something that always confuses me, I guess it's a random notation, you have this DM, which I assume is the probability of given the model given you have PM, the probability of a model with fixed parameter value, right? But I don't know how to think of just the probability of, like, say, just a model sort of agnostic of specific values. So is this purely my degree of belief that, do I believe more of a model that is lambda CEM or lambda CEM with some extra degree of freedom? Or does that make sense?
We will come to making statements about different models and how to compare them later.
I think that's a statement related to evidence sometimes.
Yes.
So
Yeah.
If we'll come to that now.
Yeah. So just a trivial example. Of course, we all know how Jacobians work, but if we have uniform priors in uppercase omega m and h, transforming to the physical matter density in h leads to these non-uniform priors. If one wants to choose uniform priors, you really have to think about what parameter space you want to visualize afterwards. Of course, the beauty of uniform priors is that when you then plot, just say in this case, omega m prior versus posterior, it becomes very clear what the impact of your prior is. You either hit a boundary or use in the flat part. So whatever you see in terms of posterior constraints there really comes from your data. But if you then want to compare it to another experiment measuring physical baryon density, that's no longer the case. So just one of the many caveats to keep in mind. So as you can see, most of the case, we just wiggle our way around and say, let's do the simple thing and maybe check later. Is that a question? Yeah? Okay. And at least I would say in large-scale structure analysis, in many cases we do the same. Hopefully it will be okay, fingers crossed, for the likelihood. So that is now the likelihood of the data given parameters and the model, where at least in large-scale structure we typically say, well, we have so many data points that the central limit theorem will come to the rescue. And we're averaging over so many Fourier modes that we then assume a Gaussian likelihood. And that is mostly a matter of convenience because the alternatives are really difficult. Of course, the more general thing to do would be to look at the chi-square distribution, similar to some of the low L likelihoods in the CMB. But doing the proper mode counting for that, especially when you go to more modern summary statistics, gets almost impossible. So at that point, if you're doing an explicit likelihood, this is almost impossible to check. But in certain limits, like doing particularly two-point correlation functions where you know the exact pair counts, one can do the proper non-Gaussian likelihood, which has been explored recently in quite a few papers. And they found that, at least for the current generation of surveys in weak lensing and angular clustering, this is definitely not among our high priorities. We are in the limit where there's a large number of galaxy pairs, and also where in weak lensing the stochastic noise is high. That helps. But with simulations becoming cheaper and cheaper, there is alternative approaches, in particular likelihood-free inference and simulation-based inference, where we directly use simulations to generate samples, and at that point don't require an explicit likelihood or covariance. So we can use these approaches to cross-check results. But that's a lot of work. Yeah? No, there we will have to do a voxel-based likelihood, very similar to CMB low L. So even if we go the simple way of a Gaussian likelihood, we have to find some way to evaluate it. And because of the complexity of these models, the likelihood can rarely be written in a simple closed form equation that you can just plot directly over a large parameter space. So at that point, we have to rely on indirect methods. And while evaluating it at every point in space on a grid would be the most straightforward, this is computationally really impractical. So at that point, we will rely on sampling methods or on Monte Carlo methods to do integrals for us. So if we just want to take the ensemble average over some arbitrary function g of theta, over ensemble average over some distribution p, of course, that's easy to write out as just integral over g of theta, p of theta integrated. And the main trick then is that if we have samples of theta that are distributed according to this distribution p, then we can evaluate this integral as a simple sum over the samples. That's just simple Monte Carlo integration, which means that you will want to do MCMC whenever you want to evaluate integrals. So this works great to get a mean, to get say uncertainty quantiles. This is not a good method to get the best fit. For that, we need other techniques. So in order to do this now, we will need to find some process that gives us these samples distributed according to our distribution, according to, say, p of theta in that case. And for that, we rely on Markov chain Monte Carlo. But the Monte Carlo part here just refers to the Monte Carlo integration. And Markov chain now means that we will have some set of events where each element depends only on the directly prior one, not on the states before. And in that chain, the transition kernel has to satisfy a few conditions. So we need to ensure that we have detailed balance. Equal probability that if going one way versus backwards, and we need ergodicity. So that means that it must be possible in principle to reach any point where our PDF is non-zero, and also to return to a point where the chain had been before in finite time. But this does not have to be a periodic process. It just means that if you run your MCMC long enough, then you will cover all of the relevant parameter space. That's not really easy to do. It is more something that you can check by running very long chains. As far as I know, I don't know of a direct algorithm that ensures it. It's just something to check off your chain afterwards. Which directly also brings me to my point there that there is a certain lack of definiteness that the chain has converged. In the end, we can do our homework and try this in many different ways, using different starting points, using a bunch of different samplers, and make sure that results hold, especially if they're surprising. But you can't prove for a given chain that it has converged. And again, similar to what I said about HUD codes, it's useful to write out a simple version yourself once to make sure that the key concepts really settle in. But after that, Again, public code is your friend. There is quite a collection of samplers available in the public domain that are optimized for particular applications. So depending on the type of problem, you may want to use something more similar to standard MCMC, or you may have a problem where, say, nested sampling techniques are better suited. So depending on the problem, you will probably find a sampler that works out of the box and saves you a few months of coding and validation time. But if you implement the basic thing once, then Metropolis Hastings is a useful thing to do to just get the basic idea. So we are at some point in our Markov chain at some parameter p, and then we propose a move. That is, we randomly draw some delta p from a proposal distribution and evaluate the likelihood ratio between that proposed update and our current point. If that ratio is larger than 1, then we in general accept the move, meaning that we have that we are just automatically moving to regions of higher likelihood. If the likelihood ratio is less than 1, that is, we proposed a parameter with a smaller likelihood, then we accept that with the probability R. And in practice, we implement that as rejection sampling. So we generate a uniform distributed random number and accept if the random number is smaller than our likelihood ratio. And if it's larger than the likelihood ratio, we reject the move. If we reject the move, that means that we stay at our current point and append that to the chain again. So as an illustration, let's just say we are at this point and then do a random draw from our proposal distribution. If our proposed new point is in a region of higher likelihood, we definitely accept. And if we move out to the region of lower likelihood, then we do the rejection sampling to decide whether we move. And because this rejection sampling is proportional to likelihood, that means we may accept regions that are not too much of a step down, but are very unlikely to accept points where the likelihood ratio is considerably smaller. That directly tells you that you have a multimodal likelihood with different islands. Transitioning between those can be difficult, and you'll probably want a specialized sampler. So clearly, to make this process efficient and not just do small steps around the same region of parameter space for a long time, or to reject most proposals, that means that this proposal distribution needs to be tuned to the problem. And of course, the ideal proposal would match the shape of the underlying distribution. But that's, of course, what we're trying to find out. So we can't implement that in practice. But we can do an iterative procedure and try to get closer and closer to something that gets to the desired level of efficiency. There's many different ways of tuning proposal distributions. One that's fairly easy to picture is that you can run a short initial chain and estimate the parameter covariance, and then use that to basically define a new proposal distribution for next iteration. But at that point, you have to throw away the first chain and only use samples from after the tuning, because the first part of the chain and after the proposal update are no longer in detailed balance. Now, especially in large-scale structure data analysis, we typically find ourselves in high-dimensional spaces. For DES, we typically sample of order 40 parameters. You will see tomorrow how many parameters there are in the EFT of large-scale structure. In some of my simulated analyses for Roman and LSST, I've used close to 200 parameters. With a fairly slow likelihood. So in that sense, there is quite a few parameters, not just our standard lambda CDM parameters. And at that point, we'll have to think about how to do this high-dimensional sampling efficiently. One approach would be nested sampling, where you start with a large number of points and then repeatedly eliminate and find new replacement points, which is implemented in the popular multi-nest and polychord samplers. And one nice thing of these types of samplers is that they calculate Bayesian evidence along the way already for you, which is something that we will need for model comparison. Unfortunately, choosing the right sampler for a particular problem is an art and very hard validation work. Again, as I said for catalog level systematics earlier, that this might be multiple person years in a large collaboration. In DES, for example, I would think this was more than 5 person years to really get sufficient agreement between different samplers. So here you just see 2 different nested samplers running on simulated data. So a case where we really know what to expect, synthetic data, so we really know what to expect. And then it took lots of tuning and running chains again and again to make sure that at least these 2 nested samplers shown in red dashed and blue here kind of agree with each other. And a lot of that is just brute force, try different settings, try again, and make sure that our results don't depend on the sample settings. Not glamorous work, but essential. If we now think that we have found a sample that, or once we have confirmed for ourselves that we have a sample that works for our problem, then we're in business to interpret these chains. Of course, the first thing we want to do is to check whether we actually found a good fit. And then we want to quote some cosmology constraints to check if we've broken lambda CDM yet. We may also want to compare with other similar measurements and compare with independent experiments, none of which are as straightforward as it sounds. So let's first talk about how to report constraints. Unfortunately, papers don't come with VR goggles, so we can't just send everyone the 40-dimensional posterior to inspect for themselves. Instead, we have to break it down for a publication. That means that we're limited to 1D or 2D marginalized constraints. So we integrate out most of our parameters from the posterior and project onto a subspace, which then may look like this whisker plot. Of course, something we've all seen a lot, but unfortunately, a lot of information can get lost in this projection. And in certain cases, this visualization does not really capture the information that we intended it to have. Let's just look at this toy example comparing 2 data sets, where in the 1D marginalized case, you would say, oh, all great, these 2 data sets agree. But if you just go 1 dimension higher, you clearly see that supposed agreement is a projection artifact. In practice, it's rarely this drastic, but these type of projection effects are a persistent problem in analysis with lots of parameters. So, for example, using purely synthetic data generated exactly by the analysis model, we know that we expect a perfect fit at the ground truth. But when we then do the high-dimensional inference, the marginalized posteriors may be skewed from the input, even though the map point is pretty much um, on top. So here's an example of synthetic DES analysis, where you don't even see the difference between the truth and the map in some cases. So the best fit clearly recovers the underlying parameters. But when you then look at the marginalized constraints, in this case marginalized over about 28 parameters, you find that the posteriors are skewed by, in this case, by almost a sigma. And that is purely because we have to visualize them in 1D. That is annoying and affects many current analyses. But that's a problem that entirely goes away with better data. So if we kept the model fixed and just increased the data, the volume of our surveys, this would all work out. So here's an example of an EFT of LSS analysis, in this case with synthetic BOS data, with both different nuisance parameter priors. So blue and red are two different sets of priors on the EFT parameters. And then the solid contours repeat these analyses after increasing the volume by a factor 16. So between red dashed and blue dashed, you can see quite significant differences in certain subspaces. But then in the far future, if we had 16 times the BOS volume and were able to just continue with the same model, this issue would go away. But of course, likely if we go to more constraining data, we will need better models with more parameters. So this is an unlikely limit. And that's exactly why I initially also mentioned frequentist statistics, because they can provide a useful cross-check. So in a frequentist analysis, mm-hmm. So I mean, this marginalization happens afterwards, both whether you do nested sampling or classic MCMC, you will do that inference in the full parameter space, and then only afterwards marginalize.
Yeah, I'm just saying that like, if you want to calculate the mean quantity, right, in a high-dimensional parameter space,
Yeah.
so you probably want to use a nested sampler and not an MCMC and then do the integration. Like that's the entire idea of nested sampling. I understand. Maybe also, but if this is correct, so how can we use an MCMC result set also the 1D multi-analysis? Because that's like figure suffer from the same problems.
I think we have a disconnect right now, but I can't pinpoint it. Yeah, but again, in classic MCMC, you would generate a chain in the full parameter space, and then afterwards basically integrate out the additional nuisance parameters. Now, in a frequentist analysis, we would use a rather different approach. That is, if we want to get rid of nuisance parameters rather than marginalizing, we maximize likelihood over those nuisance parameters. So that means that we evaluate, that we try to find the likelihood as a function of our parameters of interest theta, and then just choose the values for the nuisance parameters that maximize that likelihood. This is a technique that's quite common in high energy physics and used more and more frequently in cosmology in the last 10, 15 years. This is particularly useful, of course, when you're hitting prior bounds. Now, of course, in a frequentist analysis, it doesn't make sense to talk about priors in the Bayesian sense, but there can still be hard limits, as in this example, the neutrino mass definitely being larger than 0. So you can't really explore the parameter space to the left of that bound. And bunching up against that prior in the Bayesian analysis would lead to a lot of distortions. While in this profile likelihood way, we can really evaluate all the way down to the hard physical bound. And then use that from that to construct upper limits in this case. Again, coming back to the EFT of LSS and with the application, was that a question? Okay. With the, in the context of BOSS, because that's the LSS analysis that we're doing here. Here's a nice paper comparing MCMC and profile likelihood analyses for this data set, where the dashed lines here are the posteriors estimated from Bayesian inference, and the solid lines are the likelihoods from a profile likelihood analysis. So you can see that there is quite some spread at the moment, but as in the case with unconstraining priors, this issue will resolve itself with better data or with more constraining power. At the bottom, they repeat the profile versus MCMC analysis, then which is just the blue case from the upper panel. Again, for 16 times the Boss volume. So in that limit, when you have enough constraining power, then you should get consistent results from profile likelihood and MCMC. Of course, there's quite a question of how you would actually interpret the error bars of the profile likelihood in a cosmological context. And that's not what I want to advocate for here. But I think this can be a really useful diagnostic to understand whether your data is actually constraining enough for the type of inference that you're attempting to do. So definitely something that should be on the list of things to check afterwards, especially if there's a surprising result. And there's, for example, quite a body of literature doing this comparison of Bayesian inference versus profile likelihoods in the context of early dark energy. Now, the next step that we may want to do is compare different models. And the simplest thing, of course, one could do is compare the best fit and just look at the chi-squared for two different models. But that does not include uncertainty or a penalty for having extra degrees of freedom. So at that point, we will now need to think more carefully about that denominator in Bayes' law that we've ignored so far. So typically when we just do simple MCMC, we know that this is a PDF, so that needs to be normalized. And we can simply ignore the denominator. But instead now we really need to quantify this probability of the data given our model. And of course we can rewrite that again as an integral over prior space, as putting back in the prior, saying, okay, this is now the joint probability of the data of parameters and models, and then our prior for parameters within that given model. And we integrate over the parameters. Since the posterior is usually small compared to the prior, this is really hard to evaluate. But If we do this, then we can start looking at the ratio basically for different models. So at that point, we of course have that the probability of model 1 given data compared to model 2 given data. That depends exactly on this evidence ratio and priors on the two models. The question then still though is, even if we figure out how to compute this, how do we really interpret it? This standard literature there is that we will favor model 1 with R to 1 odds over model 2. Sorry, typo. And typically the threshold has been saying that if this evidence ratio is larger than 3.2, that is a substantial evidence in favor of model 1, and R/10 is strong evidence. However, unfortunately, these numbers actually really depend on the prior volume. Before just using the Jeffrey scale blindly, we need to understand whether the prior volumes associated with the two different models are vastly different, because that can really skew the interpretation. And then we can also extend this to think about combining data sets. Where at that point we have to differentiate sorry, somehow I have 3 typos on the slide, I'm really sorry. If we want to combine different data sets, of course, there is some that will have the same model parameters, and others may have different model parameters, which complicates the setup of comparison. So, yeah. I mean, the Bayesian analysis does not differentiate between parameters of interest and nuisance parameters. And then we can decide whether to combine or not, again by building an evidence ratio between these the joint and disjunct analysis. But one thing that turns out to be really important here is that the collaboration or any analysts should agree on the threshold for inconsistency beforehand. Somehow, when results are marginal, one could say not that interesting, that's when telecons tend to get heated. So in order to bring an analysis to the end, it's really useful to decide on a threshold for inconsistency and make a clear plan beforehand which type of data sets you want to combine. Otherwise, if you have a marginal result, then picking which data set to combine with or not can basically direct you into different corners of parameter space. The final ingredient in this inference that I haven't discussed really yet is the model itself. And of course, that is very dependent on the particular analysis. But I think one general statement we can always make is that no model will be perfect. Of course, in our dream world, we would just get a bias-free parameter estimate with statistical uncertainty, and by some miraculous way, we would know that we're right. Now, in practice, if we now just test this model on mocks, we might directly realize in the first iteration, oh, I'm not recovering the truth. And after doing some checks, we also realize it's not just a prior volume effect. So that means there's some systematic effect that is ignored in the analysis, resulting in a parameter bias after the inference. Yeah? Mm-hmm.
So I was wondering, let's say we have some big calculation, and what do you think is the best way to proceed? For example, if we are in DES or DESI or Euclid and we want to add CIE data up, then we would need to like within the whole collaboration to agree on this threshold of like each peak project and then include this range, not the other way, it's like way too hard to actually agree on something.
I mean, at the end, the collaboration has to, basically people in the collaboration have to sign off on this number. But at least in my experience, this is typically not discussed, say, for the first time in a plenary at a collaboration meeting. Rather, a few experts will look at it and make an informed proposal, which then people sign on to. But otherwise, you will just have the same chaos afterwards. Yep, there's a lot of things that one should really plan before doing the actual opening the box and looking at the actual data. I will talk a bit more about that tomorrow as well, when I'll also briefly mention blind analyses for extra fun. So here we realize we have ignored some systematic effect, and we'll do some research to identify it. And the result of that research, ideally, would be some kind of parametric model so that we can marginalize that systematic effect and at that point remove the parameter bias. But of course, because we've introduced additional parameters that we marginalize over, our error bars increase. And that can be a substantial effect, of course. So at that point, it might be time for yet more research that is coming up with meaningful priors on these new nuisance parameters, so that we regain some of the constraining power. Okay, that would still be a serious dreamland, I would say. In practice, basically, pretty much no model will be perfect, so we will be left with some kind of residual uncertainty. And of course, we will do our best to really quantify this residual uncertainty and maybe improve the model. But in practice, the situation to deal with this is to throw out some data points. That is now the final ingredient for the inference that I want to discuss today, that is scale cuts. Of course, we can measure power spectra, correlation functions from very small to very large scales, but we only use a limited range of them in the data analysis. And on very small scales, that's often due to observation systematics. For example, the imaging systematics that I showed you this morning. While on nonlinear scales, the nonlinear modeling of both bias, retrospace distortions, or baryonic effects in weak lensing is what's truly limiting us. So that means somehow from our model misspecification in the nonlinear regime, we need to come to a set of scale cuts that basically keep the impact of these model shortcomings under control. And the standard way of developing these scale cuts is to do parameter drift tests, which the model method of choice, of course, would be mocks if we think that they are sufficiently accurate in a nonlinear regime. Or we can also do it on data if it's allowed by blinding. So plot here just shows you parameter constraints from a massive simulation, the PT challenge boxes for halos, and then the parameter inference for different scale cuts. So that is for 0.14, 0.16, 0.18, and 0.2 h over megaparsec. And you can clearly see as this analysis goes to more nonlinear scales, especially the bottom right plot there, you see this drift where analyses get biased because we push too far in a nonlinear regime. So from these tests, then one has to develop some set of scale cuts. And with that, I would say we are then all set for parameter analysis. And I'd like to conclude this lecture today with a comment on systematics limited constraints and what that should actually mean. Of course, it's easy to say that if we were in a statistics limited regime, then we know how our parameter constraints scale with simulation volume. That is just with square root of simulation volume. And that, of course, is for a fixed galaxy sample, same model, same summary statistics, and probably assuming a Gaussian likelihood. So basically, if we were going to just analyze a small subset of the boss data and then the full one, in that ideal case, without nuisance parameters, we would find the scaling. However, in practice, the improvement from better data is much slower. So if you now think about the type of analysis ingredients we discussed today, when we think about our actual parameter posterior, depending on the data, and also explicitly on K-min and K-max, includes marginalization over systematics. And if these systematics are prior dominated, that means that the part of the parameter constraints that comes from this marginalization will scale much more slowly than with a root of survey volume. So in that case, basically that means that going is much more slowly when we're prior dominated. And the real forward in that case is not more survey volume, but improved calibration of these priors with either external data or simulations. And on the topic of scale cuts, if these are determined to limit parameter bias, as in the example of the drift plot on the previous slide, that means that at a fixed tolerance of parameter bias over statistical uncertainty, then our scale cuts will get more rigorous as our uncertainty decreases. So as the data gets better, K-max gets smaller. And that again means that the improvement in constraining power is much slower than square root of survey volume. So that really means that at that point we have to improve the model with as few additional parameters as possible, so that we keep K-max as similar as possible. And in this picture, I would say basically all large-scale structure analyses are systematics dominated, simply because we are throwing away so much information through scale cuts, and because priors are so important. But that's also a good news for data analysts, because this clearly tells us that statistical power is not everything. And we don't need to fight as hard to keep every single galaxy. So sometimes reducing the volume or number density a little bit to make things simpler may actually also lead to an improved analysis. And that's particularly true if we throw out some galaxies that are particularly hard to model. I mean, the footprint of the survey is often cut to somewhat increase homogeneity and make the mask more regular. So that's one way where data is thrown out, especially at low completeness. And at least in spherics, we're definitely throwing out quite a few galaxies. Yeah. But and similar in DES, we're also throwing out a lot of galaxies. In that case, BOSS and DESI, where the target selection does most of the work, is different. But yes, so with that I will conclude today, because I'm at the end of what I can, of how much I can speak today. Sorry. I hope I've shown you some of the key ingredients in parameter inference, and that this is actually a major research project by itself also, It's not just a case of running one particular sampler and then going with whatever result you get. Hmm?
You wrote this Gaussian likelihood at the start, so how do you estimate the variance?
That, of course, depends on the particular analysis. In DESI right now, they're using an ensemble of mocks. In DES, we use analytic covariances. BOSS, I think, also primarily used easy mocks, but then Jay Weidecker showed how well those agree with analytic covariances. So there is not one general answer. Yeah?
You normally do these statistics because you assume that you have like one sample of quasars or whatever it is. What do you say about your systematic in these forecasts?
That's an excellent question. And I think also a reason why many people disregard forecasts in some sense. In many forecasts, for example, the scale cut is rather arbitrary. At that point, it really takes a lot of expertise to understand which forecasts one should trust and which ones are more an exercise in Fisher matrices.
So I have a question about the sampling techniques. So you talked about the fact that you can run into issues when you have high-dimensional parameter spaces. Do you think that weighted-based sampling techniques, such as different multi-dialog, can help with this?
Yes, of course, they are designed to help with this, but at the moment, still many of our likelihoods are not auto-differentiable. Yes. Okay.
So about skill kits, for example, how are these exactly determined? Mostly if you look at like the DES skill kits and like the KIT skill kits, then DES has the reputation to be like quite conservative usually. But then what's the rationale on that? Like, ideally you have like one skill kit that's just the best, right? But then apparently that's obviously not the case. So
Yeah, and I think that's also why it's so important that right now we have these three different collaborations in friendly competition. In weak lensing, we currently have DES, KITS, and HSC all doing similar analyses. And we constantly reanalyze each other's data and learn a lot from each other. Of course, when we say here that, for example, we would determine scale cuts based on inferred parameter biases, that is still a threshold that we choose personally. In that sense, the question is, what are the collaborations comfortable with? KITS also for a longer time had included some level of AGN feedback in the baseline model. So that allowed them to have a more aggressive scale cuts. In the end, there's just a lot of moving parts, and different people will come to different approaches and solutions for this problem. Because there is no one obvious answer except, well, be super conservative, stay in the fully linear regime, and then you don't get any constraining power.
Okay, I really don't see any more questions now.
Thanks.